Why it's not? So let us quickly finish we finish the things we can cover. Please fill in when you have time, but you, I mean, because I still see not every people fill in, so I have to make it assignment to make sure that, I mean, you would do it. So the goal today, of course, is to finish lesson 7, but I think I can because we not entirely finished 6, so I just go back a little bit and talk a little bit about 6. So one thing that I where's the phone? Okay. One thing that last time I feel like I should give a slightly more detail is the pseudo R square, because I think I just scratched the surface and the textbook doesn't mention it, so I didn't mention it, but I figure out that I should have covered that as well. Just the pseudo R square, how they are being measured. Okay, and so probably you remember R square will be something like this, right? If you still recall, hopefully it would be fine. R square, when you learn, suppose I have a simple linear regression, I have bunch of scatter point, right? The scatter point is like this, right? And then if I try to have a regression line like this, right? And this is our estimated model, right? Alpha hat plus beta hat x, right? And each point, right, is actually from data, right? So the data, let me use data, right? The data, suppose this point will be xi, yi, right? There's no hat because it's from data. And remember, when we compare R square, we are looking at the benchmark, which is the y bar, right? Which is, we're explaining y without looking at x, right? So that is this guy, right? I hope you still remember this guy, right? Suppose this is the y bar, right? This is the y bar, right? Y bar, remember how we do it, just sum of yi over n, right? And the model that should explain is what? We are expecting the model to tell us, to explain this green area, right? The green is yi minus yi bar, right? And usually we care about the square, right? And of course, we care about every single point. Then this is the summation of the point, right? And this is known as usually SST or TSS, depend on which textbook you're looking at, right? And this is the part that we want our model to explain, because the very basic model will give you the purple line, right? And you want to explain the green part. And your model is able to explain, what color should I use? Orange, right? Maybe this is the part your model explain, right? This is what? This is yi hat minus y bar, right? And you care about the square because you don't care about up and down, right? And you care about sum of all points. Sometimes it's called sum of square regression, okay? Or sum of square explained, depending on what textbook you're using, right? And R square is simply the ratio of the two. R square, okay? And this must be 0 to 1, okay? And although I've drawn in 2-dimensional 1x and 1y, but this thing holds for any x, any y, because it's just changed to the plane, okay? So this is something that if you look at my undergraduate notes, then that's already there, okay? So this R square it only makes sense when you talk about regression, right? When you talk about logic, it's not really something, it's not it's not the best because logic, the reason why logic doesn't hold, because logic doesn't have the idea of this one, right? It's not an appropriate concept because it's non-linear. So things is not really, you can still calculate that, but it's not really something that we look for, right? And logic, there are several ways to measure. One of them is called the pseudo R square, which I actually add that to your slide. It's not in the textbook, but I add that because I think some of you asked me. I think it's important. So the pseudo R square, there are many types. Okay, you can look at Wikipedia. There's many types, but the most used one is the Manhattan one. The Manhattan R square is simply the R square is defined 1 minus a ratio. Okay, and what is this ratio? Is the fact that L is the likelihood. So remember what's the likelihood? Likelihood, I mean, probably have to go to the likelihood first before I understand what's going on. And I go back to the likelihood. I think we mentioned a little bit, okay? And I add a slide because I think that would be a helpful one. But this is, if you learn from your undergrad, that will be the same thing because this is exactly the example that I mentioned in the class, right? Suppose you have a coin, okay, head or tail. You don't know the probability whether you end up more likely to head or tail, right? If P is more than 1/2 or less than 1/2, the coin is biased, right? If P is 1/2 except 1/2, then you say fair, right? The question is, how can you infer P from the data, right? And of course, there are several ways to do it, right? One way we mentioned, some of you have learned undergrad, it's called method moment, right? So basically, you just calculate the sample average, and then that equalize to the population average, and then you just estimate the parameter. But we're not going to that route. What we're going to do is talk about what we call the maximum likelihood estimation. Okay, although it's a little bit more convoluted, but I guess that would be easier. Okay, so the simple thing is like every time the coin gives a head, right? So I have a random variable which head means 1, tail means 0. So the second bullet point is clear. And so if I know the P, right? Suppose I know the P, then probability of Y equal to 1 is P, right? It is 1 minus P. So this is the model. Okay. Maximum likelihood is the idea that you have a parametric model. So you have a model, you have probability model. There's some parameter to be estimated. This is P, unknown parameter P. Okay. So we try to figure out that given the data we observe, what should be the most likely P, okay? So if you try to, I want to use, I'm not tall enough, so let me grab something. So you combine these two, it's this guy, right? Because when P is 1 minus 1 is 0, so it's gone, right? And when Y is 0, this is 0, this 1, so get rid of this guy. So this is just summarize this two. Okay. And the question is, okay, given this knowledge, okay, how can we try what we're going to do? Okay. Remember, we want to try to find the unknown P, right? So we define likelihood of P will be a posterior, given what you observe, what's for the P, okay? So basically, it's this guy, okay? And you assume each one is equally likely, each observation is independent, so likelihood, we just multiply this guy. So do note that the difference of maximum likelihood is you know the Y, which is data either 0 or 1. You try to find the P such that to maximize this guy. So that is called the maximum likelihood. Okay. So basically, we just try to find the best P to make sure that the realization or the likelihood is the highest. Okay. So Now you understand likelihood is like if you don't want to look at the math, the likelihood which simply means that I try to figure out what's the P that best fit the data. Okay, and the idea is the following, right? This, right? You can imagine that, okay? You have a bunch of data, yi, right? Y, right? You have some of them is 0, right? Some of them is 1, right? Sometimes it's 0, sometimes it's 1, right? Your bunch of 0, 1, right? And based on this, right, you will have a depend on the P, right? You can calculate the likelihood. Okay, calculate this. And you try to figure out, depend on the P, you try to change the P and try to change this this bar graph, okay, in the way that the likelihood that depend on P will be maximized. Okay, so that will be the idea. And let's go back to the logic idea. How do you calculate the this guy? Okay, and the easiest definition is look at the denominator, log likelihood. Okay, and this guy gives you what? This guy is the model that without any model is same as the regression you have a intercept. So it's an intercept model, right? So look at the intercept, okay? How much the model explain? So there's a baseline, right? And this is the model you have, right? So, and then why this is the right thing, okay? So the why you have something like 1 minus, why you don't have this guy? The main problem is the likelihood is between 0 and 1. All right. So you take the log, that means what? Negative, right? Because if you remember the log, it's like this, right? You still remember the log, right? Likelihood is between 0 and 1. The likelihood can be anything, right? But the log likelihood, okay, will be something like this. Right? This is, I think you learn in the, you can go up her, but anyway, it doesn't really matter anyway, right? Log 0 is 1, right? Log 1 is 0, right? So just you can go up, but you see the smaller this one become more negative, right? It's bigger, right? So why you have to adjust for this is because if the model is useless, right? L and L log will be same, right? Because your model cannot improve likelihood, right? So they're saying that it means 1 minus 1, 0, right? So that's why useless, 0, right? If your model is very useful, to think easily means this one is very, very small, which means that go to negative infinity, right? And this guy will be super large. Sorry, this guy will be 0 because this guy is super negative. This guy will be some number, right? Some number over very big, that is going to be 0. So it is 1. Okay. So that's why you have to make it this way. Is that clear? Of course, you may ask why it's not this over this and you're done. But anyway, this is how they define. So I don't have anything to say. But understand why they define this way. Of course, there's some reason why they define this way, but it's out of our scope. But you just need to understand the pseudo R square is very similar to the R square you talking about, right? R square talking about the compare the case when you have a horizontal line and your model, right? Here the same, this horizontal line compared to your model. Okay, and of course, the pseudo R square, the bigger the better. Is that clear? Okay, I add one slide to this, and so basically, pseudo R square will be used when you do logic and profit model. Okay. And The other one is called another way to measure is called the deviance. And also I talk about this because the Python I think Python export this, I don't know, but anyway, the textbook has that. It's just -2 times the likelihood. Okay, and of course, likelihood is negative, right? So of course, deviance is a bad thing, right? So the more DVA is worse. Okay, and of course you can look at the mean square error, right? The same thing, but this is measured in terms of likelihood, right? That's why the next one I want to talk about a little bit is actually we will do today as well. We will call the AIC and BIC, which also in the Python output, but I didn't actually mention it, but I probably should have mentioned it now. So if you understand the likelihood, here is the deviance. Okay, the only difference is the deviance. The only difference is look at the complexity of the model. Okay, if you want to say the more parameter is not so good, right? Because the simpler the model, the better. Okay, remember the AIC, BIC, the deviance, the smaller the better, right? So the likelihood, right? The higher, the less negative, right? Because it's an increasing function, right? So that means that you want this one to be as small as possible, right? So you want to use the P is the number of parameter, the smaller the better. Okay, and the only difference here is 2 become ln depending on the sample size, and usually today we talk about statistical model, doesn't really matter which one you use. And I think the textbook recommend the BIC, but usually doesn't make a big difference because you are choosing model using the same set of data set. So usually you don't really matter that much, but if you really want to punish the complexity, then you want to use the BIC. The textbook recommend this one. Okay, we'll talk about how to use this more today, but that is the model that I want to mention because it's not entirely there. And I think we mentioned this Berea score, which is measuring the each observation prediction minus what you actually observe and square. This is actually the basically the let me go back here. It's actually this guy, right? If you look at regression, but not regression, but I mean, we're looking at this one. This guy, right? This guy is yi hat minus yi square and fh, right? Sometimes the book we call SSE, right? And if you find average, sometimes it's referred to MSE. Okay, it depends on the textbook you use. Sometimes it's very confusing. I mean, here I have the sum of square error, sum of square regression. Some of the book will say sum of square explain, use this one, and some of the residual put there. So have to be very careful how you use. I think I use this is follow the Excel because I teach undergrad, so I just use the terminology in the undergraduate. But depending on what you learn, so have to be very careful what you're actually reading. Okay, but that is the look at how. This is looking at how deviation, right? Actually, from that one, right? We'll talk about this today more. Okay, the loss function is a loss function, and another one I want to mention because also appear in your Python is called the log loss. Okay, the log loss is will apply for profit and logic, but it's a little bit convoluted. Okay, let me explain a little bit. So if your data yi is a data, right? Data is only 0 or 1. Remember, 0 or 1, right? And if your prediction is correct, which means that yip should be, suppose y is 1. If your prediction is correct, then yip should be 1. Right? Because your data should be same as predict, then it's the same thing, right? Let me repeat, okay? Yi is either 0 or 1, right? It's binary data. Then if your prediction is correct, YIP should be also 1, right? Consistent. It means that if this is 1, so if this is 1, this is 1, log 1 is 0. So loss is 0. 1 minus 1, 0. Okay, so there's no loss because you predict correctly. If your Y is 1, your YIP is 0, right? That means that, wow, of course, it's usually not 0 because your prediction is not exactly 1, right? Because when you run the logic, it's usually never 1, right? It's almost close to 1 anyway, but this one will become positive because log of this guy, right, is probability. Somewhere not 1, right? So this is positive, right? There's some loss there. And I said this is 1, so this is gone, right? And if your data actually yi is 0, this is not there. This is not 0, right? But you predict, if you predict 0, then it's fine. Log 1 is 0, then you predict correctly, there's no loss, right? But if you predict is 1 or close to 1, right, or not exactly, then there's positive loss. Is that clear how this is being done? Okay. I make a table. So yi, the data, okay, yi can only be either 1 or 0, right? Whether you have or you don't. And your prediction, okay, should be what? 1 or 0, right? If this is what I had, P, okay. Actually, I mean, should be 1 to 0, right? Because you're looking the logic. We're talking about the logic, right? So it's between 0 to 1, right? Your data is only 1, 0, but your prediction probability can be anything between 0 to 1, and it's very unlikely you have 1 or 0 because the way the logic works, you never, because the infinity, right? So you never have 0 or 1. But anyway, it can be as close to 0, close to 1 as possible, but you can never get 0 or 1 if you consider the case of a logic appropriate. Okay, and let's consider these two cases, the extreme two cases. Okay, what would be these two numbers in this context? Okay, if your data is 1, okay, and your prediction is 1, so 1, 1, log 1 is 0. So the first guy is gone. Y1, 1, 0. So it's 0. Okay, so we predict correctly. So this is 0, right? And similarly, if your data is 0, you predict 0, you predict perfectly, right? So look at this, it's the same. So 0, forget about it, right? And log of 1, 0, right? Log 1, that is 0, right? Right? So this is 0 as well. Okay? And I will try to argue that they are infinity because you're completely wrong, but never, and don't worry, but this is an extreme case, never happened, right? So if your data is say 0 and you predict 1, anyway, remember you never predict 1. You only predict go to 9 anyway, but you see what I'm saying. So if you 0, right? And if you predict 9, right? That is very close to 1 anyway, right? So this doesn't really matter, right? Because 0 times anything is 0, right? And this is 0, right? Is 1 minus very close to 1, right? 0.99999. Log of 0.0001 is very negative, right? So negative become positive, so very positive, right? So that is very big, very big. When you close to 99999, right? And similarly, if you have 1 and the YIP is very close to 0, okay? So what you get is the second term is gone because this is, you put Y as 1, so this is gone. And this case 1, and this is very close to 0, right? Log very close to 0 is very negative, so very positive. So basically, you are what you're putting is they are all, this is 0, this infinity, and this is goes up, right? So this is how you are being measure this log loss. I want to mention this is not because I want you to remember the formula, but just want you to know that the thing exists in the Python output, right? If you still recall, in the Python output, where is Python output? Here, right? You have the log likelihood pseudo R square. Later we talk about the BIC, AIC log loss. And this is something you want to look at. So that's why I want to mention the pseudo R square. Okay, it's not because I create something you want to remember, but if you read the Python code, you want to understand what's going on, right? So I hope, I mean, you don't have to understand every single output, but I think because today we need the BIC, AIC, this kind of thing anyway. So I just talk it here. Okay, we'll talk about this again today. Okay. So I hope it's more clear. Okay. So let me quickly finish this time series regression. I think we almost done with it, but we still have something not there. But let me quickly finish, but because it's not something very big. Okay. Oh. I should have reviewed this first, but anyway, the binary data is basically is the regression where you have a binary data 0, 1, right, on the Y, and you can use linear model, that's fine. But I have told you that sometimes it's good to, for prediction purpose, is to consider the case where it's not linear, but follow a logistic or a not CDF or normal, and that make or prediction is between 0 to 1. Okay, but between 0 to 1, that never 1, never 0. Okay, then make our prediction easier. But of course, nonlinear model make our interpretation more complicated. Okay, but that is the thing. So I'm not going to go. I think I go through everything there, but you just remember, you just need to know how to run the logic, right? Because that would be something trivial. Okay. Now, for time series regression, as I mentioned in our class, we don't actually touch very deep in the regression because we touch the surface, and we will talk about how we do some of the regression. Okay, but we don't talk too much difficult one. So just to remind yourself what is time series. Time series is observe something over time, and as an IT manager, you often have this data. You have a look at, I mean, the server, right? The traffic, right? And it's all a time series data. Or consumer data, someone buy your product, the purchase basket history you have is for a single guy, it's a time series data, right? And probably you ask, okay, well, so what time series, why we need to worry? Because just run the regression, y and x, you're fine. And there's some slightly issue, but if you learn undergrad, you know, when the regression, we assume each observation is independent, and that means that our interpretation of coefficient will be fine. Okay, but if the observation are correlated, you run the regression, it would bias, it's not good. So we need to have some adjustment. So basically, all econometrics, I would say not all, but most econometrics will be saying the idea is run the regression, but with some kind of adjustment. Depends on that. Profit is like y is a little bit different, right? And you want to maintain 0, 1, then you have to do it, right? You have to do the logic and profit. Here, when we have the time series model, we'll have some adjustment on the functional form, make some data cleaning. We still run the same thing, but using different estimation, different adjustment of the error, right? Remember the standard error, you have the simple version, you have the robust version. And here we have the robust time series kind of standard error. So it's not complicated, but just kind of new rule to remember. You just need to it's like a recipe, it's a cookbook. So it's more like our class is like don't teach you the details, how to cook, okay? We just give you a microwave. You just need to see, okay, this I press this button, this I press this button, okay? I'm not going to change in the chef because only one class, okay? But what we're trying to do is, okay, you see you want to cook this stuff, okay? You press this button, the thing cook for you, okay? That is use of Python, okay? We don't teach you too much detail because of the time constraint, and you are not going to be a data scientist anyway, right? So you're a manager, right? The scientist is your staff, right? So you have to know what they're reporting, right? You don't need to know how it's being done, right? You just need to look at the food, taste the food, whether it tastes right or wrong, right? Not to actually cook it, okay? So that's the idea. So this is frequency is a timeless observation, and very important is called the first difference. Is to take the difference between one observation to the past period. Okay, so I don't talk about in this class, but here I just focus on absolute difference. You can easily imagine the relative difference as also a case to study. Okay, and the trend. Okay, you can see upward trend, downward trend, linear trend, exponential trend. And why you want to care about this is because when you have trend, your regression will be wrong. Okay, so that's why all the time you have to detrend your data. Okay, and there are many ways to detrend. Okay, because of why we need detrend is because all time series analysis would require, at least the basic one, will require what we call the stationarity concepts. Okay, we require the time over time. The object is not going to change, right? If the object is changing, then the data is useless, right? Because what we remember, why we need to use data, right, is to generate pattern we learn from the data to the case that we haven't met or we want to know, right? From the small picture to big picture. If the small picture is changing all the time, right? So there's no bearing, there's no point. So that's why stationarity, we have to assume, we cannot check, but you have to take a belief, okay? Believe that it's not going to change, okay? If something changes, the data cannot be used, right? Imagine that the data you collect from the COVID for internet, right? For your IT manager, right? Suppose to collect data for Alibaba or Tmall during the COVID. Okay, look at the consumer data or server data. Is it going to be available now? You can tell me, right? Yes or no? Probably not, right? Because that time things are different from now, right? Right? So things change, right? People say, right? When man or woman got married after 7 years, things become different, right? So it's just like things are different after the thing change, okay? So you have to be very careful what to do. And the general time series model, we would be very careful. One thing is called the correlation, okay? But the reason is the correlation of this will be very useful for us to decide our regression formula. Okay, later you will see. Okay, and of course, if this guy is more or less zero, then probably you don't need to worry about time series model, right? Because if there's no trend, then you can safely use regression. Okay. So this is the as I mentioned, this is usually the most. I mean, if you learn time series model, this will be the standard model you learn. It's called AR1 model. Is what today's is a fraction of yesterday plus this. Okay, and then you will be surprised that why I talk about this model, and this model indeed turned out to be surprisingly, for prediction purpose, at least for the macroeconomics, this is one of the best model you can imagine compared to complicated model. If you try to have there's a paper trying to say you learn many economic model, try to compare prediction result. This beat everything. So if you try to figure out the time series model, that's the best. Okay. Surprisingly, I mean, So in the particular case, which this is one is everyone care, is the random row is 1. Okay, and this is the model that every econometrics break down. Okay, because in this model, the past, okay, today's is same as yesterday plus a random. Okay, it's a random walk, right? And for this one, okay, you can never do anything if the data is a random walk. Okay, so that's why we need to have a what we call the unit root test. Okay, and I don't want to go to detail on this because this is super complicated. Okay, and if I want to talk about this, I probably need several classes to talk about this. There's no way I can talk about this. But what I want is to tell you, you want to check whether your data is a random walk. Okay, and there are 2 different tests, which I would say, even by looking at the name, is very scary. So the one is called the ADF test. The other is called the KPSS test. Okay, and don't worry, you just need to look at the P is more than reject the null or not reject the null. That's very simple. Okay, and do note that these 2 tests has very funny thing. It's just reverse. Okay, the ADF test, the Omitted filter test, is you want to reject the null. Okay, if you know, then you're happy, then you're done. Okay, and for the other one, KPSS, you don't want to reject it. Okay, and if you learn statistics, actually there will be infinite many tests available for you to do. You can do either one, should be fine. And they are cost and benefit using these 2, but I'm not going to go to detail. I want to mention this because they can easily implement in your Python, so that's why I mentioned it. Okay, and so the way I use is to use the stat model API. Okay, and this I generate random walk. Okay, you don't need to worry about this because it's not a time series class. You can just take it. You can just consider this as your data is a Y. Okay, this I generate random walk model, but you don't have to worry about because I'm not talking about simulation anyway. But if your data is a data Y and it's very simple, you will see just one line. Stat model dot time series analysis, and then the key Omitted the key filter on the Y, and that's it. Once you do it, you can tell this is an object. The first item is a T stat, the second item is a P, and then you check the P whether it's more than negative, less or more than 5%. That's it. Okay. And the other way around would be similar. If the KPSS, you just into KPSS, that's it. Okay. So it's nothing very deep here, and the way is if you have a random walk, how we're going to do? The solution is instead of regressing, probably I didn't write that clearly. So instead of your model, okay, instead of using Y, T, X, T, say suppose, right? This is a model you think, okay? And if you figure out Y is a unit root, okay, then what we're going to do is don't use the Y. Instead, you use the delta Y, and that's it. Okay, that's very simple. You check your data only wherever the Y, okay, if it's a unit root, okay, or random walk, right? If random walk, take the first difference, which means that you don't look at the Y, but look at how Y changes, right? You don't model that. You don't model the Y, the level of Y itself. You model the changes of Y, right? If change of Y, the delta Y is past the unit root test, past the random walk test, then you can use it. If not, do it again. Look at the change of changes. You difference enough, then you will get what you want. Okay, that is a standard procedure. Let me repeat. Okay, if this has unit root, you take a delta. If still unit root, delta again. Unit root, delta again. Delta until it's done. Okay, so basically the economic meaning, the intuition is you cannot model the level because level is like it's not stationary, but the growth rate should be stationary, right? Just look at the price of the stock movement. Usually, if the price is like crazy, right? It can be random walk, but the return of stock is not crazy. It's going to be a stationary. It's not going to be got super problematic, right? Because the rate of change is much stable concept than the price alone. Okay, so that's the idea. But anyway, I doubt as a IT manager you would be having a unit root. This is usually a unit root is a problem of time series data, and so financial time series data, and unless you are doing a platform for a cryptocurrency, probably no more job anyway. But those kind of stuff, right? Otherwise, you don't have to worry about this. Okay, so it's not something that, but I have to mention it because every textbook mentioned it, right? And I don't think it's useful for you anyway. But that's why it's very brief here. But here the following three is you should pay attention because this is relevant, right? Because your IT manager, you have data from a platform, data from the IT. Very often the data is time series and it's over time. And over time you have to control season, days, and hour. Otherwise your regression is not good. It's not perfect. Okay. So what I mean is the following, right? Very simple. I don't do too much math here. So if you want to have this, right? This is your model, okay? And your data is time series data. So you just don't run this pure regression. Instead, you add some dummy, right? Usually, say, I don't have month. Okay, you can have year dummy, right? Then remember of the COVID data, if your times data of COVID is fine. Put a COVID dummy here, right? 2019, 20, 21, 22, right? They'll be controlled. That's no problem. Okay. So even you have a data, you think that there's some year, there's some problem, that's no problem. Just say dummy. If you think that day of the week is a problem, right? Sunday, Saturday is different from the weekday, right? Weekend is different from weekday, no problem. Do it. Okay. An hour, right? Also a problem. Suppose you are the IT manager for Tencent, right? The game platform, right? And you know that after 11 p.m., no more games can be played, right? But still adult can play, right? Like you guys, right? But no, probably you guys are studying anyway. But after 11, the data will be different, right? So you would have to put dummy on that. Okay. So that is important to control. And so I think I mentioned it already, right? So that is a random walk and trend. I mentioned you take the delta, then you're done. And dummy, we're done. Okay. And the last thing that we need to control, then I mentioned last time, is called the serial correlation. Okay. And the problem of this is this guy. After this, we'll break. Sorry, a little bit longer. So this epsilon t, okay, is the thing that we didn't measure in our model, right? Suppose I want to explain, well, how much money a guy spending on my game platform, right? Say, then probably I can see how old they are, right? And how much he spent in the past and so on and so forth, bunch of stuff, right? Control many things, right? And where he live, the province he live, right? And many things, right? And but no matter how you specify the model, you will have something you didn't know, right? For example, I don't think your data, even your IT manager, will contain the macro variable like say whether there is someone win Olympic Games, everyone will happy, or Chinese football team win a game, everybody will happy, right? And this, right, will create called serial correlation because like Chinese soccer team win some game. Some people happy today, happy tomorrow, and so on and so forth, right? Several days happy, right? And they related, right? Or some person, right? You cannot capture, you can't see he may be winning a lottery, maybe he got admitted to the dream school he want to, or he met a new girlfriend, right? He lost a girlfriend, whatever, right? And these are correlated, right, over time. But you can observe, you can print the model. So that's a problem. So how we solve this problem? Very simple. Just like we do the robust standard error, just what we call this Newey West standard error. Okay. And the implementation is very simple, which I stopped last time. Is you have time series 1, okay, and I shift 1 drop means I call lag 1, and I do the lag y, and you don't have to lag, but I just do the lag. You don't have to do that, but that I just make it. The regression I'm running here is the delta x over delta y. Okay, the regression I'm doing here is dy. Okay, and okay, why I do that? I mean, you don't have to do that, but sorry, it's lag y. Why I do lag y? Doesn't really make sense anyway. Why I do that? Oh, I see why I do that, because I running the I run the first difference regression. Okay. But anyway, I'll explain what I'm doing here. But the thing is, like, this guy is the key. Okay. So this is the one. I have the HAC, and then I have the maximum lag of 1 Newey West, and this number, I think the standard they use is 5 as big as possible if you want. Sometimes they recommend 7 to 19, and this lag you can adjust as big as you want. And this lag means that how the epsilon are related. Okay, so within 7 period they're related. Okay, then you put 7, right? Suppose you imagine that the unobserved effect epsilon have 7 period distance have the effect, then you put 7, right? Suppose you imagine that the effect is like someone met his girlfriend, okay? Then he happy for 7 weeks, okay? Then you put 7, right? If you think that you think your something unobserved is like take 3 weeks to gone, right? Maybe Chinese soccer team wins, then the guy happy for 3 weeks, then you put 3. Okay, there's no hard and fast rule to do that, but you can put as large as possible and just try to reduce. There's no particular thing. I'll explain why I have the FD regression for this model. Or I omit the point. Okay, so what I do in that one is this model. Look in the first difference. Okay, and because the trend. Okay, so the idea is why I run this model is because of usually the unique root problem, right? I run this, okay, and this model have a random walk, okay. So I cannot use x to explain y because y is like changing too fast, okay. Random walk means they change too fast. So what we're gonna do is instead of using x to explain y, I use change of x to explain change of y. So that's the usual thing you do, okay. Of course, sometimes you may just want to, the model depends, maybe something like this also fine, okay? You can use x to explain y also fine, but I don't know. Anyway, and there are more stuff, but I think I'm safe to skip because I don't think that would be very useful in our context, because I think I just cover the this time series. Just want you to have a more complete understanding. So don't worry if I skip, means that they will not appear in your assignment or exam. because I think time is more wise spent on other things. Because today we talk about more prediction that will be more useful. So if I have time today, I'll go back, but otherwise I will just skip. I'm sorry about that, but first time I teach, so I don't know actually how much material to cover. But I think it's okay to skip because I think I covered the main thing already. So let's have a break of 15 minutes and we'll come back. So since we finished time series, next week we have a short quiz for this topic and before. The quiz is a multiple choice, the same as we've done. Nothing special, just multiple choice. Okay. Ai, 好難教啊，好難教啊。喂，一齊咁。因為呢啲沒事，嗱，我帶過嚟嘅。開埋咧，有啲少禮咯。係咪要啊？有人要開過嚟攞？啊？真帶啊？做完算數的嘛，對吧？可以。主要可以借拿。我帶嚟400啊。我感觉真的。哦，明白。对面大会相关的呢，你们在哪？我在。而家都冇啦，呢個一般講法，但係你話你應該有冇啲壓力啊？應該再 cut 嘅，我已經 cut 咗好多㗎啦，其實已經。因為我覺得我出嚟可能太少，所以可能太多人。佢哋班教。佢哋班係咪多？我一樣教好多嘅。教啊，咁都所以大家重點係我哋。即係你諗，我哋一年係3個成，即係本身啲嘢已經錯得快，跟住嗰個成就對得快，根本上學唔到嘢。喂，講真 undergrad 我有成有 revision bit， 搞翻中文點解？即係年3就係好大個問題，就係我搞嘅文字嘅嘢會做得太水，搞得太難嘅頂頭，我好難。
所以就好難。
大家覺得容易啊？對我嚟講，我其實因為科係冇學得而家，對我都差唔多。可能佢哋對佢哋嚟講簡單。
有啲人話係
係，
所以我就覺得好麻煩，你明唔明？所以我就覺得好困難搞，搞多啲人，搞少啲人。而家找下嗰個問題，我哋 reflect 下咯，我可以下年我再教佢可以。
真没想到从事真迹的这个事。
我大脑都是用在一个没有技术、没有用的东西。哪里有？
我以为他会死。
基本上在 IT 的这个。对 IT 的。基本上都直接跟得上去。然后还会在这个现在就是经常然后到时候就可以讲。把这两个然后加一点，最好的挺好的，就是我还是不解释这个花这个我的花的basic apple 对。对，我要去跑一个把那出没有，我都没有跑。对啊，然后我说到后面都没有，就我自己都不知道我没有必要教。我应该我相信对数据的打实战的。IT manager 的话，在 data。
这课出来要其实肯定。因为我开 time series 课，就专门教我 time series。每人都问。
我也有。
那我这边。我说你现在我改啥呢？好，无人来。但是我没有改，都带了回。就是应该了解的，知道我跟大概了解我。
今天看他们就 criticize 说这个越来越复杂的模型，但是他们都不好解释这个东西，并且是现在非常长，所以大家都比较简单的模型。但是
LLM 的方法简单，
大家都在做这个，
去把那个直接做到还有人在做 I'm serious。 他应该没有新的问题，没有新的问题，肯定还有新的问题，也会做了，可能今天还要来。我不懂我到了，他的那个啥东西，我为了记忆不上。我因为上班，对，还有到有 transform 一下 variable。
我是真的，
感觉应该。
我能去给他练。
打这个，哎呀，飞下去。反正大家都很累啊。都。
没
有啊，就别人聊不起来。不然大家都累的好的。出去。我今天上了2天，我感觉都是有的班长没有来。
魏老师，你现在上课搞这种，然后你期末搞
背刺了，
背刺我。
No， 我们。
然后又给我一瓶奶茶安慰一下。
我那个，我从来考试都很低，所以没有问题。
那我就给你评价，你该给我就给你满分。
考试不改，也有10秒。cái lục dâm yêu người yêu người.
So, so some of you mentioned worry about our tests. Looks like we cover so many stuff, and then it's not very easy. But I do want to emphasize our course is applied. So as I said, the main thing is trying to give you the Python output and ask you to interpret given the result. Okay. And probably make it easier. Maybe I would try to ask some Python code in the sense that I give a Python code and ask what is it doing, this kind of stuff. Not ask you to write the code, but I give the code, you try to tell me what it's about. Make it more manageable. And I hope that would. I know you guys are very busy, so I do understand. But especially when you do programming, I do understand. I mean, it's like black hole you suck into that thing for a very long time. So try to make it more manageable. So let's see if I got anything from you. Next time we should use Python or R. Next, you mean the next? I mean, you can use Python or R for your assignment or your exam, whatever. There's no restriction. But I would focus on Python. R, if you want. I mean, later I will make a tutorial for undergrad. If you want, you can go. But or the TA make a tutorial. But Python will be fine. I guess the Python would be I try to do Python because you told. I said again, I do Python not because I want to do Python, because you learn Python in the summer. So I don't want to teach R again. Actually, R will be easier because to handle data. So, but looks like it makes everyone difficult, but I don't know. Hopefully it's easy. No question. Learn fly before you can walk. That's true. Some of the problem we have is like we only have 12 weeks, and then we have to basically cram, I think, more than 8 to 9 courses into this one. I mean, actually each chapter probably is a single course can be made into single course. Each topic we cover as a single course can be made. But I don't know. I'm not the one who decides the course, right? So I can just try my best to deliver things that the symbol are difficult to understand. Okay. If you still have questions, let me know. I try to help as best as I can, because Python is formula is abstract. True. I do think the formula is very abstract, and do remember that our class do not require you to reproduce the formula. Okay, the formula I want to give is you understand the logic behind. Okay, intuitively, and then you just want Python, because I'm pretty sure when you go to work, you will never see the formula except look at the menu. Okay, and at that time you need to understand. Say, remember how I understand that, right? If you go back to this idea, okay, and look at this, okay, you don't need to understand why this formula works, right? Just the formula there, this formula. You need to know, okay, in the extreme case, this happened. This happened, and what does it mean? How to use this? Is R squared, the bigger the better, and that's it. Okay, of course, even though you forget about this, you only need to know R squared bigger the better. The level 1 understanding. Level 2 will be try to understand this. There's a formula, it's a ratio, and level 3 will be okay. What is this? It's a intercept. It's a full model, right? And 0 and 1, right? 0 refer to what, 1 refer to what. I mean, I think my slides already so condensed. It's like bare minimum. But you can read the book. I think the book is very well written to understand the more logic. But this is the thing that I think the minimum that you need to know, right? The R square, the AIC, BIC, right? If you don't want to care about formula, doesn't really matter. Don't ask the formula. You just need to know what they're doing. It's the likelihood and the punishment for the complexity of the model. The more complex the model, this guy get higher, so the model is less favorable. The minimum you need to know, you want this 2 number as small as possible. That's it. I mean, I give you the background because I can't have a master class say, okay, there's a measure, smaller, better, and a measure, smaller, better, and a measure, bigger, better, done. Of course, I can do that, but you don't learn anything, right? You want to know something, why this is true, what actually they're doing, right? And then you can say more, right? I can make it baby style, but it doesn't worth your tuition, right? So I need to give you some background, but at the end of the day, this is, you remember, smaller, better, that's it, right? When you actually use it. You don't even remember the formula. And I don't. I mean, if I don't teach this class, I don't get it back. I know somewhat like this form, but I don't actually recall that formula. Okay, I just put it there, right? Just there. Okay. So I hope kind of make you Feel happier. Today's not sunny. Yeah. How old am I? Good question. It's slightly almost 40, slightly below 40. Good question. But you can guess because I studied undergrad like 20 years ago. Yeah, 20 years ago. 20 years ago, I'm undergrad. It's difficult to calculate. It's easy, right? Okay. Make sure today is Friday. Okay, not Tuesday. So if you're still sleepy. Whoa. Okay, sunny, rainy, cloudy. Okay. We don't have a consensus here. Time series regression, yes. Time series regression, AIC, stat, yes. But that's good, but I think not for this class, right? There's no key point. I think we have key point. But anyway. Oh, I think that's good. Take enough sleep. That's very important. That's very important because the time series problem, right? Not enough sleep is correlated. You will be carry over for your not enough sleep. Will carry over to the next period, affecting your performance. So it's important. You see real correlation. Puppet logic, that's good. Random walk, key. Okay. I have somewhere funny result. Okay. I think most of you think it's okay. I love your, okay, thank you. Shanghai index. Oh yeah, I think this is a very good joke. Not joke, but I think this is a number that I have when undergrad. Yeah, they said defending for 3,000 for 20 years ago. So when I was a student, this number. Now it's this number again. So it's a good joke. It's cool today. Yeah. Thank you. Yeah. Thank you. But I got married already, so can't get married again. If I get married again, then probably I go to jail. So yeah, happy 99. This one, yeah. I want to go to seaside. That's simple. It's very close. But be careful. Trick or treat. Oh, that's too early. Too tired. Oh, I don't think it's a joke, but it might be. Okay. Okay. Thank you. I hope that's make you a little bit awake. I like the jokes because happy is important. Right? As an economist, right? What we learn is maximize utility, maximize happiness is the most important thing. Lifetime happiness. Okay. So today, what remaining time we talk about lesson 7. Don't worry, it's more conceptual rather than calculation. We have some conceptual at the end, but the main idea of today is a very hot topic. We call prediction and the linear regression, and is the reason thing we call machine learning or AI. All these are basically on prediction. Okay? We have some X, we want to predict Y. Okay? And how to figure out the best predictor, how to select variable, is the thing we want to use. And don't worry, LISO is like kind of regression, okay? But we have some term there. But don't worry, it's not, nothing is complicated today, the remaining. So everything is just very conceptual, okay? Very conceptual. So framework of prediction, okay? And so far we talk about how X and Y are related, okay? And we are not particularly interested into prediction. We're interested in how they're related and get some understanding, okay? And here we have much more important goal is to predict, okay? Is to get what we want to have. Is as an IT manager or product manager consultant, I think that's very important, right? We don't too much care about whether X Okay, it's related to Y, but rather with the X, it helps us to predict the Y, regardless they're useless or not. Okay, you can imagine I want to predict, okay, Y maybe suppose I'm 20 years ago, right? I met a beautiful lady. I want to predict whether she loves me or not, right? Fair, right? Fair enough. And predict her variable X, right? Can we depend on how much money I have, right? How handsome I am, what are other my characteristics, right? Just run a regression like this, right? Fair. But if I want to predict what the other X I have, right? I has which month I'm born, which day I'm born, which year I'm in, what are the might be where the location of star, right? Or whether I have some lucky number, right? These things might help, right? Fortune teller style, right? So you are now become a fortune teller, right? You don't care about how X and Y related, okay? You just care, okay, X can help, right? That's the idea, okay? It's not try to have a explanation how explain Y by X, right? Rather, anything useful, I can use it. Okay, so that's the idea. Okay, and there are two terminology we introduce called original data and live data. Okay, original data, as later you will see, is a data that we try to build our model. Okay, and live data is the data that we would being try to use it. Okay, later you will see more carefully. But you will see. Okay, it just later you will see more carefully. Okay, so another, there are several motivation. I mean, some of you mentioned I should give more examples, so hopefully there's more example here. So you want to sell your car, you want to say what kind of prices you should do, right? So it doesn't matter whether the price related to whatever. You just say, okay, this help us to get the right price, and that's it, right? You don't really care about actually they are how Y and X are related. You don't care about theory in some sense, right? Just how the best way to predict. So for example, I'm an IT manager here, right? Airbnb, right? You want to how to price the stuff, okay? Or if you are IT manager, what kind of algorithm you're going to put into display, right? It's a question. And maybe you are, some of you mentioned about ITM is about consulting, right? Exactly the consulting problem is looking at there are several firms asking for loan, which company you should give loan to, or how much you should give, okay? Which firm is likely to success or not, okay? It's a prediction model, okay? You don't really try to understand X and Y, but just interested in just getting the result, okay? So there are several type of prediction. I think we have learned that in the topic 3 about interval estimation and point estimation, right? X bar plus minus 2 SE, right? If you still remember interval, you predict it just that itself, right? Just the quantitative one. This is the most useful one. And we just covered the probability or logic is the probability prediction. It's a probability, right? You just end up in saying the probability of someone who buy the stuff is some probability given their characteristic, right? That is the IT manager you do. And these are all very traditional probability or statistic idea, okay? And classification, okay, on the other hand, is usually called for prediction model. And you just I don't really care about probability, okay? I don't care about whether it's 1 or 0, okay? I'm not interested in probability. Just tell me whether 1 or 0. Okay, tell me this guy is going to buy or not buying. Don't give me his buying with probability 0.8. I don't care. Give me 1 or 0. Okay, that's called classification. And we cover this? Maybe we cover some of this. Okay, I'm not entirely sure, but this is one of very important machine learning way, right? Is just to predict 0 or 1 directly. So we will be standard machine learning class is we will talk about error first, because that is do prediction. That is the thing you try to evaluate a model, right? Because there are, for every machine learning, you will see huge number of parameters to do, right? Regression is very simple. You can see just we have k regression of k variable with k parameter. But for machine learning, actually you will notice is there's a lot we call hyperparameter, and then later you will see is way more thing you can calibrate. So that's why you look at this one, we call the predict one minus the y, but this is same as regression, right? The regression is the horizontal line, right? Let me just go back to this one. The errors like this, the same as we have been doing all the time, so just don't worry about that. Nothing new, it's just this guy, right? This error. So this is a good take. This is error. Okay, if you want a regression model, this is error, right? So the question is how we evaluate this error. Okay, because you try to fit the model, right? Whatever model you can fit, you're going to evaluate this error, right? And you try to see how you are going to fit different model based on different error. Okay. So, and this error, usually look at the book, they will tell you there are 3 types of error you can have. Okay. The first one is called estimation error. The reason that you got is because they call overfitting, underfitting, or model bias. Okay. Underfitting, model fitting, the idea is very simple. Overfitting would be you use the sample to predict the small picture, predict big picture. Overfitting means that you are trying to get too much out of the small picture, because look at the detail so fine, which this detail, the pattern, is actually not in the big picture. Okay, let me repeat the statement. Okay, you are trying to infer from a small picture to a big picture, right? And you read into the lines too much. Okay, okay, it's suppose right, I try to infer the quality of this brand based on what I drink, right? Okay, so now if I try to infer that, okay, I drink it, it's a milk tea, right? And because I want to infer this is a whiter brand, right? I try to infer from this idea to the whiter brand, correct? And if I take into too much of whether they use good milk tea or good kind of sugar level or not, then I read too much into the sample. Okay, and because I should look at how in general how things being done. Say suppose maybe here they have one typo, right? And I say okay, oh, this guy have one typo in this package. Then I try to infer the quality is very bad. I overemphasize the special feature on this, right? And to ignore the whole general pattern. Okay. Okay, that is the idea. For example, look at this maybe example like this. Okay, at the data, okay, what you have is something like this. Okay, okay. And okay, suppose your population is like this data, right? X and Y, okay. And happen to be your data is here. Okay, happen to be surprisingly. Then you just overinterpret. You think that actually the regression should be something like this. Okay, you overinterpret, then you make a wrong thing. It's fitting. Okay. Later you see basically just like you think that is the pattern appear in the data, but actually it's just some random error. You fit too close to the thing. Okay, and underfitting is just reverse, right? Because you don't take into account of the pattern enough, so you miss something. And model bias, right? There's a model, you fit the wrong thing. Okay, the other is called model error. Okay, and the simple idea is the following, right? You try to fit a linear probability model to a CO1, right? And at the end you get a probability more than 1, then you're wrong, right? Or suppose you use regression, you use the probit, right? You should model is a continuous variable, you just fit the wrong model, right? And the last one is called a genuine error, which means that this error is coming from the epsilon, coming from the thing that you can't measure, is you can't really avoid it, right? Maybe, for example, right, you try to measure how people use I don't know what you want to kind of predict. Maybe predict the web usage, right? How people play games, right? And the error, how maybe the X is like you predict how much time people spend on playing TV games or the mobile games, right? But happen to be there's some power outage, okay, or the internet breakdown, okay. This you can't control, okay. This is the thing will be into your model, right? And you don't know, right? You can't control it. So random as well, you cannot control, right? Or you try to measure something, right? And then we know there's a cosmetic background, radiation can change stuff. Okay, this is the idea of a genuine error, which you can't really, even if you have the best model, you can't avoid. Okay, and the more you can write better model, you can avoid. Okay, and in this one, to be very careful, the machine learning, very often you overfit. Okay, because you fit a lot of things that is actually not there. But anyway, later we see. Okay, and we will have, usually we do the contrastic loss function. It's not surprising this is the one that you use for regression, right? We have been using this regression, right? Take the observation over this is square, right? Square loss. Okay, so this is the one that actually we use all the time for when the regression. Okay, and we can look at we compare model looking at the MSE I mentioned already, right? You have model A, model B, and you to say whether A or B is better, look at the MSE or the RMSE, right? Of course, the smaller the better, right? Because it's the error, right? So that is something. Later you will see, we will compare the example, then you will see we compare this guy. And this is what we call the decomposition. Why? I hate it. Sorry, I mean, I update the slide, but it's not there. Anyway, it's fine. So the MSE, okay, can be decomposed in 2 parts. Okay, always. You can decompose into, I don't bother the math, but the first one is bias. The other one prediction error. The bias is how your data different from the mean square, and how your data versus so this is the so if you say you can look at the regression. Let's go back. It's easy, right? This is y bar. This is y hat, and the data here is yi. Okay, and you will the MSE, right, is this guy, right? And you can look at by decomposition. You can look at This is called bias. And this is the prediction variance. Okay. And turn out that you can always decompose this into these two parts. Okay, very surprising, but it's a math result. Okay, and why is important? One of the main thing in machine learning is you will be trade off these two. Okay, if you want higher, this will be lower. This lower, this will be higher. Okay, so that is the that's the idea. Depending on the method you use, sometimes this is smaller, sometimes bigger. Okay, and that is always a trade-off between the two. But anyway, I think that's enough for the moment. Okay, so let's look at the example. I think this is the use case would be the best. Okay, so you want to sell a car, okay, and you want to see what kind of price you want to put it at. Okay, so what they do is to get the data from the web and try to predict the price I want to sell. Okay, so you can see there's a bunch of data, a lot of stuff. Okay, because we are now in the prediction model. So basically what you're expecting to do is to have a many X. Okay, and out of which we try to pick up the best X or best formula that try to do. Okay, that's different from before. Usually in the before, we don't have too much X. But now when you talk about prediction, usually you have so much X. The problem is to choose which X. Okay, so that is the main thing. So that you see a lot of stuff. I'm not going to go into detail of each. Okay, and the problem you can see is I will have many models, right? Try to predict the price based on the age squared. Okay, age is the car age. Okay, and there's a lot of stuff you can control. Okay, the question is which model with the best. Okay, how to evaluate them. Okay, that's the idea. Now, so they run a bunch of regression, which we don't really care that much, but there's a number. But you can see the sign is almost right, so that's not a problem. We are not interested in the sign indeed. Now, because of regression, we are not interested in how many stars you have here. Okay, we're not going to say we keep this. We want to keep this because it has star here. This keep the star. No, we're not going to look at star anymore. Is that clear? The prediction. We're not going to care about whether the coefficient is significant or not. No longer care about that. We care about which one do prediction better. Okay, we need to care about whether this thing contribute more than that, whether the shape is linear, contrasted. We don't care. Is that clear what we're doing? We don't no longer care about the coefficient. Okay, and here is the different model tell different price. I'm not going to care about that. Okay, and here is the different model give you different prediction. I mean, of course, we don't care that as well. But anyway, this is at least you'll be comfortable. This is something that it's okay, right? It's between 6. The mean is very similar. Okay, but of course, you still to pick which one to do, right? You have the PI. Okay, so you have different model. Different model give you different prediction. So how do we go into think about this? Okay, of course, if you have more complex model, okay, this model may work very well within your data, but it may not work well in the overall, the general one. That is called overfitting, right? Because you estimate the model such that you fit very well with your data you are trying to estimate, but you will work very poorly outside of that, right? So to avoid overfitting, right? So you have to make sure that you just there's several ways to do it. The big thing is to avoid model complexity. So that's why you have AIC, BIC. They punish the complexity, right? You don't want to build too complex model, because complex model we capture too much thing from the data. Okay, imagine the following. Okay, suppose okay, the following is like, I want to predict. Okay, suppose a girlfriend. Okay, 20 days ago, right? Suppose I met a girl. Okay, I want to predict what kind of stuff can make her happy, right? And then you have to list of okay, this. Okay, and then you want to predict using that data to predict what happened. You met another girl, for example. But if you cater the list too much to this particular girl, right, then it can be wrong, because another girl can have different taste, right? So you cannot care too much, right? So you maybe just take too much stuff, then will be difficult. So you have to try to be careful not to be over calibrate, right? Maybe this girl particularly like particular dish, particular way, but you have to be very careful, right? If you do this again, then it will not work, right? Anyway, I hope it make the case clear. So I want to have a externality, right? Suppose if you always with this girl, no problem. But you want this to apply to every single girl, right? Then have to be cannot overfit that much, right? You try not to infer too much information from that data. Okay. Although I said girl, you can imagine boy the same. Okay. Just make the example easier. So the question usually you see this is if I make a very complex model, okay, I actually the root mean square error can be low, okay, when you fit it, because you fit very well, because you have so many features, use so many variables there. But actually turn out this variable that is not very useful. So the live data actually not very good. So that means that the less complex, usually the regression, okay, the more complex maybe like the machine learning many method. So that's usually you would have some trade-off. Somewhere in the middle would be the better. Okay, but that would be the idea. Okay, that is what we call overfitting, because you include many intricate stuff to fit it. Okay. Say the idea is like the following. Maybe this is I think it's a good model. Say, suppose I have a data of a several data points. Suppose I have 3 data points. Okay. If I try to fit a linear curve, okay, linear regression, then I will fit like this way, right? But if I try to fit what? A non-linear curve, non-linear one, okay, then what happens is I can perfectly fit it, right? So by fitting a complex model, I can basically fit whatever I want to fit. So that's why we need to punish complexity. It's because I add more complexity, I can easily fit things, right? But look at this example, right? If I fit a line, then I can't fit everything. But if I fit a curve, I can fit perfectly everything. So that's why I hope this example make it clear why overfitting is an issue. Okay, and sorry, this old slide I should change a little bit. I have the AIC, BIC, those kind of stuff. Okay, the lot loss, and they would tell us which one to pick. Okay, because they evaluate the model, right? The AIC, RMS, lot loss, Barra score, what we learned in the the beginning of the class. Okay, so now we are going to apply the concept there. We will call validation approach. Okay, it's called, you divide the data into 2 parts. They call the training set and the test sample. Okay, and the next one we will talk about is called the k-fold cross validation, CV. This is the most important one, because this is the thing that you should remember, because this is the main thing we do machine learning, cross validation. So the idea is the following. Okay, let me do that. Let me before I do that, I just do the validation thing. Okay, so how we do validation. Okay, this is actually how you do. A lot of people do stop price. Okay, so usually what you people see how people build algorithm trading, okay, is the following. Suppose it's a price data. Okay, I just randomly draw, okay. And how people build a trading system is the following. Okay, you would be using 75% usually. I mean, there's some other proportion, but 3/4 of data, okay, to train your model. By training your model is use this data to run the regression, okay, or not regression, but you can be thinking about a technical analysis, what kind of rule you buy, right? When you see this pattern, you buy or sell, okay, whatever, okay, whatever rule you want to impose need not be regression, can be any rule that you think that is algorithm that applies. Once you train it, okay, and then you evaluate, because you train the data train the model based on data, so it must be fit very well. So how to evaluate whether this particular buy-sell approach is going to work is look at they call the text data. Okay, and this is the thing I taught undergrad when I taught applied financial analysis. When I taught technical analysis, right? There's a candlestick, right? I don't know the thing, yin yang zhu, right? Candlestick, or looking at the shooting star, morning star, those kind of stuff, or you have the MACD, right? MACD and all the RSI, those kind of stuff. If you trade, then you know what I'm saying. But bunch of measurement, and you train based on the data and you test it. Okay. Of course, you change different strategy and compare the profit at the end, right? So that is how you look at. This is called the train test data. Okay. So imagine same for the regression. Okay. Suppose some of you ask me logic and profit, how are you going to choose, right? Suppose you have the same number of regressor. Then you run a logic, fit the model here, look at the outcome logic here. You can look at the pseudo R square, MSE, or Birra score, lot loss, whatever. Okay, look at the profit for this one, look at the logic for this one. Okay, compare the two, and then you can see which one to use, right? So you train here, you test here. Okay, you can use whatever measure you can use. This is a train test split. Is that okay? Okay. But this is not the one that actually modern people use it. They will use a little bit convoluted approach. They call that the one we have is called validation, and we will have a very slightly little bit twist your head. It's called the cost validation. Okay. The reason why the validation we use in the stock market in this way is because stock market is time series, right? This data I can train for that one purpose, right? And if I have trained in the beginning, test at the end, probably you don't feel it good, because I think the more recent data is more useful, right? But your data is not time series, right? In that case, you don't have to do this split, right? And there are many possible split you can do, right? That is why here we call cost validation is the following. The blue one is the training. The red one is the test. This is the thing we have, the stock, right? We train the first data, and the last we do the test. Okay, but we can, okay, not here. We can be put in the middle, right? There are many 5 scenarios. Suppose you cut the data in 5 parts, right? So every time you have the red one, you have the MSE, right? And then here they have K model. Okay, each set you have a K MSE, right? And then the 5 set, so there will be 5 times K's MSEs. And then you look at the average of this MSE. It will give you the model 1 performance, this model 2 of the model K. And you compare which MS is lowest, that's what you pay. Let me repeat, because this is very important. And this is the underlying for all machine learning approach, at least as far as we taught. Okay, we don't need to look at MSE, you can look at whatever measure you want. You can look at BIC, AIC also fine, okay? But MSE just the standard thing we use. I mean, sometimes, but whatever you like, okay? Let me repeat. Set 1 is the one we do for our stock, right? Because the stock is like, I look at the price for the last 5 years to the last year, data to train your model, and look at last year data. And that is how you evaluate the performance. And if your K model, you have K measurement, KMSE, okay? And the second set, instead of using this one, you use the second to last year, okay? And you do the same, train the models in blue and the red to evaluate. The K data set, there will be K measurement. Do this for 5 different sets, right? And then for each model, you have 5 measure, average of those, give you the measurement of for this model. Now you have 5 different output, okay? And then you can pick the one the lowest. Is that clear? And that's it. That is how you would do that. Okay. So let me show you this code. I think this code is the one that you will be using for the machine learning. I think that's important to be slow here. After this, I'll break. Okay, because it's important. Okay, I go line by line. Okay, and then probably it's not something complicated. Okay, here is we will have a Python library we call skitlearn. Is science. The full name is called the science kit learn. But they simplify it. Scikit-learn. This is the package. Okay, and this is the package that basically all the machine learning will be using as long as far as I teach. I think for your purpose, this will be good enough. I think everyone use it. Of course, if you go to Facebook or other, they have a better software, but there'll be not much different. Okay. And this one, I will import a model selection. Okay. Remember, I do cross validation. So that's why I will improve the cross validation score. And the score will be, I just include because I have to look at R square, MSE, so on and so forth. It's the improve some function. And K-fold is the K-fold cross validation. Okay. How you swap the data. Okay. And the second one, actually, you don't have to use it. I use it because I want data to do regression. So if you have your own data, you can forget about this line, right? Because you only have YX. I have that one to illustrate. I want to make some artificial data. Okay. So if you actually do it, you don't need this line because you're not making fake data, right? So this is only for making fake data. Okay. Now what I'm going to do is I have generated data. And what I'm going to do, because same as all, probably you learn Java as well, from Java as well, is I do randomization. I would, to make the regression, to make the program reproducible, I would define a random seed, right? Because probably you learn for randomization, the computer would just based on the computer clock to generate the thing. So that's why it looks every time it starts with different, right? Because what is actually computer do randomization is they have a table of number. You try to start from somewhere and try to read the number there, right? And how you randomize, because it depends on the computer time, right? But if I have a seed, it means that the starting point is always the same. So you always give the same thing. Okay. So here I have the seed set 42. And here I use this thing because I want to create a data, okay, which is Y and X, right? And make regression, I have sample size 100. And feature means how many X I have. And noise is it's not deterministic, right? Otherwise, nothing to learn, right? And random state using the seed. So it's very simple. I mean, for your purpose, you don't need to do this too, right? Because you have your own data. Okay. Don't do this when you actually do your job, right? The data input from somewhere. Okay. This is creating data. Now here is the real thing. Okay. Here is I have called the KF. Is defined the object that we call K-fold, which is I divide data into multiple parts. Okay. I divide into 6. Maybe it should be 5, but anyway, it doesn't really matter. This number we'll put whatever, that's fine, because you cut how many things you want to do. And shuffle is just usually set true because you want to cut it and shuffle it and do it. Usually it's better to do it because in the thing we do in the example there, we just determine cut in this way, right? But it's good. Then actually these are correlated, right? So they once you cut, you want to reshuffle again. So like sample with replacement idea. But don't worry about it. doesn't really make a difference too much usually. And random state is depends because you random shuffle. Okay. And here is a little bit slightly tricky. Is you have to define an object from linear regression, define the model. Okay. If you logic, there will logic. Okay. And do I miss something? Maybe I missed something. I think I missed one line there. I mean, I have to improve later. I mean, I have to import this function from the linear library. Do I miss that? Okay, I missed that one. Okay. This one actually you have to import from the linear library. You import this guy. I'll show it in the code lab after the break. Okay. So you have to import this guy. This guy is coming from the sklearn linear model. Okay, I will put that there. Then after that, you will do cross validation. Okay, basically just run regression many times, right? You run the regression based on the regression model with the x and y, and here I use the mean square error, and there's a little bit slightly complication is because the way they do is do maximization. Okay, so that's why they do the shortcut negative this. So that means that maximize the negative means to make it this more possible. Okay, and use the k-fold this one. Okay, so if you actually apply this in your work, don't worry, right? We just copy, then you're done, right? And then what you do is to print out the result, and then you calculate the mean. That is the outcome, right? Sometimes you may care about the standard deviation as well, but in our class we just focus on the mean. Okay, and then you can decide. Okay, this is your model, right? Based on this, and then can change another model. Maybe you can use logic, or you can use different x, or different functional form. Then you can tell which model is better. Is that clear? Okay. Here I have a full feature, right? Because I have x, but you can use less another set of x, right? You can do the same. Is that clear? Okay. After a break, I will do a Google Lab and then show you which code line I'm missing. Okay. Let's break of 15 minutes.你有问题吗？
这一个减去这个是加号。
有話錯，邊個冇？話錯咗，佢跟我話，係咪應該從邊個冇話錯？話錯？
没有错，但是不知道为什么。
你可以證明的，但是
那看这个图看上去感覺像是相減，但是確實就是相加的。
對，但係其實再問這個，我先把你 Google Code Lab 拿上來。他那個他其實
他每一次都截一小块，就是其他的每次都不同的样，但是这一块是圆。
对，就是他为了防止他会让我前面拿一个
他可能拿一个 batch 做看，然后有其他
都是拿来做回归。
对，做回归。这双这一块是他的手的，因为我们的回答都不演示。
那这个下面
我常每一次超选的，这样他的数据这么数据目前普遍上有这么有在不是好的，可能他们第一次会拿过来做那个validation， 剩下的是数据什么都那下一次选的时候拿数据打出来，然后下过一个，然后可能再往这块做。就打乱自己。
哦。
我是高人进来啊，我都把它呢呢度係講法咁係 set one 就叫 model one， set two 叫 model two。No， 你 set one 嘅時候 ，K 嘅 model 都叫做 model one 是嘅 model two。哦，我撈咗好耐。不同啊 ，OK， 我也錄緊另外一個我有用很多 model 嘛，你可以譬如話 regression 可以有那個 regression， 就是 regression 的怎麼說它都包。
比如說這裡你分了一個，然後這個是 model 一 model 一，然後每一個 model 1 model 2 3個 model， 每一次工作就不同了。
沒有，就一個 data 那個不同的 model 都跑在。
假設我做了，就一個是分項，然後有一個
2項過來。
然後那也就是我這個，比如說我分了5塊數據，然後我每次都拿一塊來測試。
對。
然後剩下的都是拿一個，比如說 model 1是分項，model 2是。
對。
然後我現在最後是要比較的。
上面就是 average。
是这个的平均值吗？
这个上面平均值。
这个就是上面所有的平均值，然后就
呢個 K 同呢個 K 唔同。呢個 K 係代表一個紅色。係。呢個 K 係代表有幾多個？呢個 K 應該係代表呢個係佢嘅不對嘅。
不一樣的嘛？
對啊。
不是很多 K 咯。
啊。要不然查思維啦，係咪？C 係3嘅。
啊，
一般係一般上
對，如果是 regression，MSC 基本上什麼都可以。R square 係 logic topic 就
那麼是還沒過的。
你可以用，你如果是 profit 或者 model 你可以用這個 R square。Okay。Apply to regression 就知道。In general，如果你 compare profit logic 跟 linear LPM 跟
所以还是单切入更广泛，
对，跟 AIC 也可以。有一种什么方法？对，就是 regression 的时候 ，regression 我哋不想 MLE 的话，不是 AIC 没有。有一理论什么模型的，不都这样？对，因为它就是那个 measure 不减，没有什么还嗰個 out just out regression 但係我哋冇所謂嘅。 应该就都要回来了。大闪的发现。想不到我用，而且大家都是不用。
啊，这个，
对，收拾吧。
哎呀，
不要忘，没有电脑啊，没会会炸。是哪里的？因为这个节目那就。怎么背刺了？我们写完了，对一下。然后是跟他的创造一个忘记哪个调去的，哪个就是高低分区，那个哦，那个刚刚原来是只有一个，一般就是同一个现在大概是6天的一个
啊，
然后他那个课上有讲，上个概念，啊，这个方面我谁猜的？这个标号对于一个 switch 它有4个 interface， 那因为有4个小电池，如果它说是从 I 到 C 的话，是的，然后 C 到 I 的，那你就看到一个6个小时，然后它走到这个 switch， 它就是应该记得，我刚才有讲过。对，那个讲完。
你再给我讲一遍。
因为它分两个，就是买一个 tag forward， 一个 switch tag forward， 所以这个有一路走过去。但是因为它 switch 是 self learning， 主要的它因为不知道怎么下一步是哪，所以它要发，所以就乱发。反正所以第一步先 C 的话 ，S 乱发，怎么发？发现这里那个可以啊，这样子大，它可以那这个，主要是这个 C 可以懂，就是因为它知道有一个来说他有个答案发到来，所以就会知道，因为他知道那个答案是从哪里来，就可以单知道他的啊，对，因为他会乱发嘛，所以这个 C 他每走到一个 switch， 这个 switch 他都会记录一下这个 C 的，他知道是 MAC address， 他会到个 C 的一个 MAC address， 所以像我们 S1 也有 MAC address，S4 也有 C 的 MAC address，S2 也有 C 的 MAC address，S3 也有 C 的 MAC address， 那他不是说他这样。然后再回程嘛，回程的时候，因为是开发下去，开发自己有 MAC address， 可以相当于，但是因为它相对的少 ，S1、S4、S2、S5 大概知道一直的一个在这里，所以走到 S4 的时候，它就不会这么这个还有一个小细节，反正是他来，他 S4 就不知道他，因为他知道他的大脑。好，
因为你有这个 table， 你都已经得出来了，你就看到了。
To interrupt you, I mean, break is never long enough always. I think in the slide I somehow omit the 2 slides because otherwise the Python don't know this function and doesn't know NP means, but otherwise it would be something very easy, right? And the output is like this number is the mean, right? So you will compare this number across different models. Okay. So I hope that would be clear. If R2, then use R2. Okay. The score is already included in this one, so that's why you just write that, then you'll be done. Okay. And some of you ask me when use R square, when MSE. R square is only defined or is well defined for linear regression, right? So if you have different linear regression, different regressor, then you use this R square. If you compare, say, different type of model, right? Then probably MSE will be better, right? Suppose you try to compare logic, probit, and linear regression, right? The 3 type of model, which one will do a better prediction? Then use the MSE will best, because MSE basically is the most convenient thing, right? Because looking at how accurate your measurement doesn't rely on the method, right? And AIC, BIC can be useful because if you have to have a likelihood, right? Unless you are estimate by maximum likelihood, you cannot use it, right? So you can use a probit logic, you can use AIC, BIC, those kind of idea. Okay. And here the car, right? Remember the car example, right? With different thing. And then they use BIC, the RMSE and the CV RMSE, right? So, and of course, you probably ask, when I have regression, how can I have BIC and MIC, AIC, BIC thing? We didn't talk about that, but when we learn regression, okay, probably I should talk about that as well, because probably you should know. When I mention regression, right, what we said is we have bunch of data point, okay, and we try to fit a line. I don't know what color you have, right? Fit a line, and the way we fit is to minimize the vertical distance, square distance, right? That is called the least square estimate, least square, right? Minimize or the error, right? Minimize the squared error, right? That is what we mean, right? But there's another way to derive the same formula. We call maximum likelihood. Okay. The way to think about this is to think that instead of minimize this guy, okay, what you do is you try to fit a normal distribution here. Okay. For each point, you assume there's a normal distribution here. You can fit the alpha, beta, and sigma. Sigma square is the shape of this normal distribution. Okay. Let me repeat the statement here. A little bit more convoluted. Okay. Instead of by turning a line to minimize this, you assume the model you have is a line plus a bell curve. You try to fit the bell curve, okay? Fit it such that the bell is best fit for the data you have, right? And the control variable is the alpha, the beta, and how flat is the this bell, okay? And that become a maximum likelihood, okay? And that's why when you run regression, you can still do the AIC, BIC thing. Okay. And because you asked me, well, some of you may ask, right? Technically, why we have AIC, why we have BIC for regression, right? Because regression have no likelihood, right? How can you do likelihood? It's like fitting the normal. Okay, assuming the error term are given by normal, you can fit it. Okay, and if you learn the undergraduate statistic, actually is there. But anyway, so don't worry. I mean, probably you don't need to worry because you ask the computer give you this anyway, so you don't have to worry too much how it comes, but just try to give you the idea. So see, you have 5 different model, different number of variable, different number of coefficient, right? Because the square term here, that's why they're different, right? And you can calculate R square, right? Because when the regression, you can look at the RMSE, you can look at BIC as well, okay? And if you lose RMSE, then you would pick this guy, right? And BIC will pick this too, right? Do note that this is in sample, okay? So basically, this is based on the training set, okay? Only the training part, okay? So this is what we call the cost validation idea. They divide the data into 4-fold, right? 4-fold validation, and they tell you, right? As we do the Python, right? This is a 4-fold here and average. That's what the Python code. Just to remind you what is there. Hopefully, it should be clear here. I run this. Actually, I have this number, and I have the average. And but in this case, I don't need the SD, but this is what you get. Okay. So you can see the 5 different model. At the end, you pick these 2. Either will be fine. Just as prediction. If you use a RMSE, is that clear? And of course, didn't show. You can use the BIC, right? RMSE. That's up to you what to do. Doesn't really matter anyway. Okay. There's some, at least you know some way to pick it. Okay. And there are many ways. I mean, statistics always there are many ways to do the same thing. And as long as the way is generally acceptable, that's fine, right? No one would pick at you why you pick this particular route. I mean, you pick a route that is well accepted, just like how we do things in the life, right? I mean, there's no particular correct way, but you know which way is better than others, right? More reasonable than others, right? But you don't know what is correct. Okay. So here, just very briefly, okay, to talk about prediction. Although we do prediction, there's a very careful about we can't check it, but you should think about whether your data actually is stable. Okay, as I mentioned to you, right? If you use the data of COVID to predict what happened now, then probably it's an issue, right? And also you think about whether the relationship is still whole, right? After things change, it's still the same. Okay, if there's something in the background changes, it's no longer true, right? And although prediction, we don't care about the mechanism, right? But you should think about that as the way to do prediction, right? Do you want to use thing that is unrelated, right? If you want to predict a stock price, do you want to use the location of the moon, the sun, the Jupiter, the Saturn to predict? Do you believe that? I don't know. Up to you. But that would be things to think. So don't worry. What is left is something not complicated. Bunch of terminology here. Okay. So here you have tell you the way to predict. Of course, that is what I expect you to start for your project. You will be doing. Maybe you want to do prediction. That is the thing. Probably is one of the main big thing in our class, right? You want to do some prediction. Start the problem, right? And you have to define what is the why. How you want to measure the y, okay? And then what kind of data you want to use, okay? What kind of the sample you want to collect? What kind of y, the functional form you want? What kind of functional form x you want? Define loss function, maybe the root mean square error, RMSE, and then build different model, do different model selection like the k-fold cost validation, and do the prediction and check the result. So this is the standard procedure that you do. I think this, you don't have to follow through every single step, but this is a standard step that the book proposed. So it's very clear. We define Y, what kind of data, what kind of transformation of the Y. One thing I have to mention is whether you want to use the binary data or the continuous data. Even though what you collect is continuous, doesn't mean you have to use continuous, right? Say you look at the customer, right? The spending, you can decompose them into high spending group and low spending group, right? Look at the age group, you can also define the elderly group or young group or more grouping, right? So look at the log or level, right? Whether it's a growth rate or the level you want to measure. And later you will see what kind of thing you want to have or drop. One thing called LISO, okay? LISO is the way that we will talk at the end, is try to, if you have prediction, usually you have hundreds or sometimes thousands of observations, especially your IT manager, right? Because you record the data continuously, right? There are many aspects you can collect. So you need to drop some data, drop some feature that is called LISO. I mean, there are many ways to do it, but we focus on one called LISO. Okay. And also what functional form depend on what you know or theory or look at the data. And once you make the number of the feature or X manageable, you can start to select the model, right? You fit the model and then you do some checking afterward. Okay. So very simple. I'm not going to detail. Is whether you want to use Y or log Y, right? But one thing is a little bit, I think that in the footnote of the textbook, if you use log Y instead of Y, when you do prediction, it's not this guy. Prediction become this guy. It depends on the variance. Okay. Why the case? Because this is not normal, so it have to be like this way. I mean, in general, I don't care that much, but if you are estimating the growth rate, you have to be very careful. I'll have to add this guy. I mean, this is in the book, so there's nothing new here. Not creating new thing. Okay. So here is I have a original data and live data, right? So this is the test set, right? And this whole is the thing is like the test data, right? This is train data. Okay. And this is the one you use the prediction. Right? So imagine the stock price, right? You use the this last 5-year data, right? This last year data. This is -5 to -1 data, right? And this is data you put in the practice. Right? Is that clear? And use log or level depends on which one you would be thinking. Is important for your purpose, right? And you look at the price or log price. Okay, price it will be contrasted. Log looks like more linear. So up to you what to do. I mean, it's not easy to tell which one. Depend on interested in the level or the change of the price. Okay, depend on your question, of course. And here the question is Airbnb. So they start with the regression. So they just see what kind of, and there's the price. Okay. The apartment and they clean up only have around 4,000 observations. And this look they get, okay, the histogram look like this one or this guy, okay. And you can see this is more normal, more bare, more symmetric. So I would say this is better than this guy because more outlier here, right? So this is, you would think the data is better if the data is like more symmetric, right? The bell shape is always better than the skew one, right? Because you know, if the data is more skew, have larger tail, then it's very hard to predict, right? Because it's hard to a model that predict like this, right? It's easier to model in this way. So and here they give different type of room, will give different price as you will expect, right? So there's the feature, okay? So that means that probably you want to separate different type for different model, right? And this is how many people you can put in, and obviously very different, right? Depend on apartment or house. So that is another way you want to look at the features as well. And now what kind of functional form you can do? So let's see, okay? And you can see the many, whether the have a TV, may have family, kids, friendly, cars, cat, dog, and so on and so forth, the many features. And that is how they start doing the prediction. So they have what they do is 80% is the work set, the rest is going to be check it out, right? The whole hour. So that is how they do it. You can see they think about this 8 different model. Okay, how do you think about that is your decision. Okay, you can, of course, here this example they put 8, but you can put as many as you think that. Well, of course, why jump from here to here? Why you start from the easiest one, right? You just keep adding things, right? Getting more complicated. Okay, and how they do this, I think they are not just from domain knowledge. You think what is relevant, and coming from what we see from the graph, bar chart, pie chart, and then you can see which to add. Okay, so now you have the 8 different model. Then what they do is, as we expect, we do R square BIC, training MSE, then test MSE, right? So that's simple validation technique, right? Just divide the data into one set and the other and do it. Okay, they don't do the k-fold, but just the simple one. Okay, so as you expect, same in the last slide, right? You fit more thing. Actually, it fit very well the data, but it do very poorly in the actual one. So somewhat here is a good one. You can see, right? You can see the smaller one, not so good, right? But you go on more, the RMS is getting smaller and smaller. Maybe somewhere here is good, right? Somewhere here is good one. 29 maybe a good one. Okay, and that's what they do. They look at the M7, and they actually do the cross validation version. Okay, but you can see that is how we do. Okay, lastly, we want to look at another thing is to cut down the number of regressor. Okay, it's called the LISO regression. So don't worry, this is just a regression. Okay, but a special type of regression. The interesting part is the LISO actually means the least absolute significant selection operator. Okay, don't worry about that. I can't remember this name, just LISO. Okay, if you want to just try to impress your future boss, that is the way to remember, but I never remember the full name. Okay, right? So the good thing is, like, you can tell what X can be chosen. Okay, and this basically, as I said, is OLS regression to select. Okay, and then one thing in this regression LISO, the machine learning, as you will see later next week, is always you will have what we call the tuning parameter, or we call hyperparameter. So it's what we call the parameter. Okay, later you will check, you will see quickly. What is LISO here? LISO simply is the following. Okay, with the regression, nothing surprising, right? And minimize this is what we learned from regression. The only new thing is this guy. Lambda, absolute value of the beta. If lambda is 0, nothing changed. Okay, and what is doing here? Okay, I want to minimize this guy. Okay, which means that I want to minimize this as well, right? The second part, which means that if possible, I try to make this as 0 is possible, right? Because the absolute value, right, is negative, positive become positive, right? So I want to, although I want to minimize this, but I also want to say for things that become 0 is better. Become smaller the better, right? By doing so, things that doesn't matter become 0. Okay, so let me repeat the statement because it's very important to understand the logic of this is nothing different from regression. Accept the fact that lambda is a known parameter. You decide 1, 2, 3, 4, 5. It's your choice. Okay, positive number, any positive number you put. 0 will be standard regression. Let's put 3, whatever number you decide. Okay, and by minimizing this absolute, right? So it means that if a variable can become 0, you try to become 0. Okay. Okay. So that is the goal. That is the definition of this. Okay. So try to make that when it reduce, it can reduce, make it 0. So things that it become, they will cancel out. Okay. So I'm not going to explain in detail because even the textbook in machine learning will not teach that. Even look at introductory machine learning textbook, they don't explain why. That's what I said. Just because of this, they reduce this size as much as possible. Just that if they can put 0, they will put 0. That's what they said. Okay. Even you look at introductory machine learning textbook. So I don't think I think it's fine if I not to talk about that. Okay. And so the only thing that is here is I'll use that model. Okay, because it's simple. Here is the main thing: model dot fit regularize. Okay, I have alpha is 0.1. Alpha is a lambda in the model. Okay, this is the alpha is a lambda in the thing, and LT1 is called LISO. If you square the rich regression, look at not absolute but square, but we just talk about LISO. Okay, is that clear? So only thing is everything the same. Is that clear? So I just fit not OS, but I fit regularize. Then I just try to have an coefficient, and 1 means LISO. So I'm not going to explain that part. Okay. If you put a square, they call the rich regression. But anyway, I'm not interested in talking about those because it's beyond the scope. Okay. And this is trying to tell you the coefficient. Okay. But just what interesting you can see is they would try to put this become 0. Okay, they would try to put you usually look at the descending order. They would put things if they can put everything in the concentrate in some parameter and forget about the rest. Okay, and in general you will be bunch of 0. That is some byproduct of this very funny regression. Okay, don't ask me why we have this. It's beyond the scope of our class to explain, but very interestingly, just by adding very surprising, right? You would be okay. Why? But this is machine learning. Yes, this is machine learning. Okay, you have already learned machine learning, so you can write your CV, go home. Machine learning in the park. Just by having a lambda of this is machine learning. You're done. And well, don't laugh. I mean, even this LISO is something people use. It's actually used in practice, so it's not something. I mean, even regression you use all the time, right? So adding one this is not something too terrible. Okay. And some of you ask, how are we going to choose this lambda? Okay, that will be something we talk about later. Okay, but you just take whatever lambda, it should be fine because you put more lambda, then actually you would just make your model even simpler, right? Because the higher the lambda, you make this penalty term higher, will make more term become more 0 faster. And then you fine tune this guy, and then you would look at the performance, right? Because at the end, look at the root mean. At the end, that's how you choose a lambda, is choose different lambda such that to minimize the root mean square error, right? But we'll talk about later. There's a tuning of hyperparameter, but that's beyond the scope right now for this class. But we'll talk about this next class. Okay. And okay. And this is how you would do it by checking the, I think this is how I look at the lambda. Yes. Okay. Probably that would be the end of the day. So last slide, so don't worry. It's a LISO, I mean, because you want to write your CV as a machine learning, so I teach the whole thing. Okay, it's LISO here. So LISO, you can see the crazy thing here. Okay, NumPy, nothing special. Data set is fine. I have a linear model LISO, so I think it's fine. Just before I have linear regression, I LISO, right? And there's a model selection. I have a cross validation score in K4. It's already in the previous slide. Okay. The new thing is this two: grid search, CV, and train test split. Okay. This one is going to look for the lambda. Okay. It's a looking for the tuning parameter. Later you will see. Okay. And this guy is trying to divide the data in two parts: one test set, one training set. Okay. So what I'm going to do is I create a data the same as before, and now what I'm going to do is to cut the data into two parts. Okay, one part I'm going to do the training, the other at the end I do the test. Okay, so I work everything on the training part. So okay, training part, test part, training part, test part. Okay. And when you work in your project, basically just change this line, right? You just don't make the regression. You use your own data. Okay. And here I define LISO. There's nothing special here. I like the linear regression. So the key here, a little bit tricky, okay, is this line and this line. Here is because I want to tune the parameter. Okay, I will define alpha, which is lambda in the previous line. Look at the lambda. It's just NP linear space from from 1 to 20. Means that I have 1 to 20, the lambda. Each step I have this very small. So a very small step is a lot of possible lambda I can have. Right? Suppose I change it to 1. You'll be 1 to 20. Okay? So I just from 1 walk up to 20, each step I walk up this very small one. So I have a very fine. So of course, in practice, you don't want to use that small because otherwise your regression will be very slow. But for this simple one, it's fine. So I had a K4, it's simple, right? And I have a search using LISO, use parameter grid, okay, cross validation. So basically what I do is I do K validation, right? Use data, figure out what's the best lambda I have, okay? And once I do it, okay, I feed it to the training data. Okay. And then I tune out the LISO, look at the LISO score, then we're done. Okay. So you don't need to worry about the parameter. It's already built in the model. Basically just click and done, right? As I told you, you don't need to worry about how it's done, right? Just like the microwave oven. Then done. Look at the score, and then you're done. Okay. So you don't have to worry too much about that. Sorry, I have the same slide. One thing I want to mention another way is we call the randomized search. Okay, compared to the previous one, the only difference is this line, randomized CV. Okay, the last one I want to say is because if I look at this grid search means I go one by one, then it's very slow. Can be very slow, and if I do randomized search, it's just like I just close my eye and do something here and there and pick the best one. Okay, so will be useful. Your model is super big. Okay, because at the end of the day, this parameter will not be that matter anyway. Okay, but you want to pick the best one. This is the thing you do. Okay, if you don't want to tune your parameter, then you just do this simple step model. Just put the parameter, then you're done. Right? But if you want, then you have to be a little bit more careful. Okay, so what they say, Airbnb, they pick up the M7 and do the LISO, so on and so forth. Yeah, I think there's nothing very special from the end, but I'll talk about this diagnosis next class. But basically, you learn machine learning already today. Okay, of course, there are many things as well, but you know this is the thing. What you do is just put your Y, put X there, right? So enjoy the weekend. Be careful. I mean, when you walk the hill and mountains, don't get lost.